Hey there, welcome back to the channel. Today we are diving into something absolutely amazing. Building a database MCP server that's like having a competent database administrator that can handle multiple databases at once. Picture this. You are juggling three different databases for three different projects. You keep switching connection strings, constantly worried about running queries on the wrong database. Sound familiar? By the end of this video series, we will have built our very own intelligent database server that works seamlessly with Cloud Desktop and can manage multiple databases like a pro. And today, in part 1, we are laying the foundation by creating our test databases. But first, let's get a quick understanding of what MCP actually is. MCP stands for Model Context Protocol. Picture it as a universal translator that allows AI models like Claude to communicate with tools and databases. It's like giving Claude a set of superpowers. Instead of being limited to what it learned during training, it can now reach out and interact with our live data, our file systems, and even our APIs in real time. So when Claude needs to query the customer database or check the inventory or run complex analytics, that's where our MCP server comes in. It becomes Claude's database specialist. Alright, let's roll up our sleeves and get started. First things first, let's open our file explorer and create a folder named Database MCP Proj. This refers to our Database MCP project where all the related files will be stored. Now, let's open this folder in the terminal. Perfect. As our terminal is open in the right directory, we now need to create our virtual environment for this project. Type python -m venv myenv. Hit enter and let that create. Once it is created, we need to activate this virtual environment. Type myenv /scripts and then activate. And with that, we will enter our virtual environment where all the required libraries to run this project will be installed. How do we know we are inside the virtual environment? Look at the terminal prompt. We should see myenv at the beginning of our command line. That's our visual indicator that we are working inside the virtual environment. If we ever don't see that myenv, it means we are back in the system and we need to reactivate the environment. All the libraries we install now will only exist in this project space, keeping everything organized and conflict-free. Now we will install the MCP library, which will help us build the MCP server. Type pip install MCP. This will start installing the MCP library. It is now installed. Let's also upgrade pip to ensure we are working on the latest version. To do that, just copy this line and paste it here and hit enter. It upgrades the Python package installer pip to its latest available version. This ensures that we have the most up-to-date features, bug fixes, and security improvements for managing Python packages. Next, we will install MCP CLI to test and run some MCP-related operations from the terminal. To install this, type pip install MCP CLI. And finally, we will install UV, an extremely fast Python package and project manager. We might need it to run MCP inspector through which we can test our MCP server. Type pip install UV. then hit enter. Now it will be stalled. Now let's open our code editor, whether it's VS Code or Cursor. Once it is opened, we will navigate to the working directory where we will have our virtual environment and where we will store all the files related to this project. Perfect. We have reached the right directory. Let's create a Python file named create simpledata.py in which we will create a program to generate a sample e-commerce database. We will need a tool to create a database. Python has this built-in library called SQLite 3 which helps us create, connect, and execute SQL commands. Let's import it. Type import SQLite 3. Next, we will import the datetime library to work with dates and times. The time delta is used for performing arithmetic operations on the dates. To import this, type from date and then type import datetime and then we will import time delta. And we will import the random library in case we need to generate random data. To do this, type import random. So these are all the libraries we will need. Now let's begin the main code where we will create our database. First, we will create a function named create user store data where we will define all the database related code. Now we will create a database connection. Now we will create a database connection. Type con equals to SQLite 3 connect and the name of the database we want to connect or create, which is sample-database.db. This code will first try to look for a file named sample-database.db in the working directory. If it finds the database, it will connect to it. And if it does not find it, it will create a new database. Now con represents opening the connection to the database. We need a medium to interact with the database with the help of queries. SQLite has this functionality called cursor, which will help us do that. Type cursor equals to con.cursor. So now we have a medium to connect our code with the database and execute queries. It prepares SQL statements, sends them to SQLite, and returns the results. If we are creating foreign keys, we need to tell SQLite to check for the foreign key relationships. To do that, we will write cursor execute pragma foreign keys, which is set to on. This line tells SQLite to start checking foreign key relationships, like making sure related data exists before inserting. By default, SQLite does not check foreign key relationships, even if we define them in our table. That means we could accidentally add data that breaks the link between tables. So adding this line is crucial. Pragma is a special SQLite command used to change how the database behaves or to get information about it. In simple terms, it turns features on or off. Now, we will create our three tables for our e-commerce database. First is users, second is products, and third is orders. Let's start creating a users table. Type cursor execute create table if not exists users. So here we are creating a table named users. And by using if not exists, we are ensuring that a new table is created only if it does not already exist. Let's create an ID column for the users table. Here we have an ID column that will have unique IDs for this table. It's defined as integer and set as the primary key, so we can uniquely identify each row. We have also added auto increment, which means when a new record is added, the ID will increment automatically and sequentially. Now, we will create other columns. The name variable represents usernames with varchar 100, meaning that it can have names up to 100 characters. And we have defined not null, which means this column should not be null while inserting values. We have done the same with the email column. The age column will have integer values, and the created at column stores when a particular record is created. It is of type timestamp, and if we don't provide a value while inserting, it will automatically fill the current date and time. We have created our users table. Now, let's create products table. First, we will create the table named products if it does not already exist. And we will create an ID column, just as we did in users table, but this time it will represent the unique product IDs. We will have other columns like the name of the product, which can have up to 200 characters and should not be null. Next, we have the description column for the product. This description is defined as text since it can be very long. Although we will use a short description for this project. Then we have the price column, which refers to the product's price and will have a decimal value. The value 10 represents the total number of digits allowed, and 2 is the number of digits after the decimal point. Then we will have a category column indicating the category to which each product belongs. For example, a laptop will have electronics as its category, and a chair will have furniture as its category. Next, we have the stock quantity column, which represents the number of units available for a particular product. Then we will have a created at column, which will represent the date on which the product was added in the table. So here we have defined our products table. Now we will create our orders table, which will store the information related to the orders of the users and the products they have ordered. First, we create a table named orders if it does not already exist. Then we define a unique ID for each order. We will include a user ID column which refers to the IDs in the users table representing users who have placed orders. Next, we have a product ID column referring to the products from the products table that have been ordered by the users. The quantity column represents the number of units of each product ordered. The status column represents the current status of the order. such as order completed, order pending, or order processing. Then we will have an order date column which will represent the date on which the order was placed. Now we will define user ID and product ID as foreign keys so that we can perform any join operations if needed. Now that we have created the tables, we need to insert the values into them. Let's create a list called users data. It will be a list of tuples containing the values for our users table. Let's add our first record. This is our first record. The first value in the tuple represents the name of the user, as defined here. The second value represents the email, and the third one represents the age of the user. We will add the creation date using random functionality in a moment. The ID column, as discussed earlier, is an auto-increment column, so we don't need to insert a value for it. Now, let's write the remaining records. We have already prepared the data in a notepad to save the time, so we can simply copy this and paste it here. These are the records for our users table. Next, let's generate random creation dates for our users. We will use the time delta function to generate dates from the past 180 days. Here, we are looping through each user in the users data list. For each user, we are creating a random date between 1 and 180 days from today. Date time now gets the current date and time. Random randint picks a random integer number between 1 and 180 inclusively, and time delta creates a time duration equal to the number of days picked. Now let's execute a query to insert values into the users table. Using insert into users, we perform an insertion operation for the users table, and we define the names of the columns into which we want to insert values. The values keyword specifies the values to be inserted into those columns. The question mark placeholders are the part of parameterized SQL queries in SQLite and many other databases. Each question mark acts as a placeholder for a value that is supplied separately to prevent SQL injection and improve performance. At the end, we add date time to the user and pass it as a value to the table. We use strf time, which stands for string format time. It is a method from the datetime object that converts a datetime into a formatted string, making it easier to read or store in a database. The string inside strf time is a datetime format. %y gives the 4-digit year. %m in lowercase gives the 2-digit month. %d gives the day of the month. %h provides the hour in 24-hour format. Capital M gives the minutes, and %s gives the seconds. When combined, this format produces a timestamp, which is a common format used for storing or displaying timestamps in databases or user interfaces. Now that we are done inserting values into the users table, we will insert values into the products table in a similar fashion. We will create a list called products list containing all the product records. We already have these values in our notepad, so we can simply copy and paste them here. Here, the first column represents the product name, and its first value is laptop, followed by a short description, high performance laptop. It has a price of 999.99. This product is categorized under electronics, and it has a stock quantity of 50 units. Now, let's insert the values into the products table just like we did for the users table. We will simply copy the insertion code, paste it here, and make a few updates. First, we will simply copy the insertion code, paste it here, and make a few updates. First, change the variable name from user to product. Then, update the insert query to match the structure of the products table and modify the column names accordingly. Next, we will move on to creating the orders table. But before we do that, we need to get the IDs from both the users and the products tables. We will use this to generate more random and valid data for the orders table. To get the user IDs, first we run the query to get all the users' data. Then we look through each row and take the first value from each one, which is at index 0. That gives us the user ID and we add it to our user ID list. Now, we do the same thing for the products table. We want to get both the product IDs and their prices. We run a query for that and then we will save the results. Now that we have all the data we need, let's create some records for the orders table. We already prepared the order records in a notepad to save time. So we will just copy and paste here. Let me quickly explain the structure of each record. First column represents the user ID. Second column represents the product ID. Third column represents the quantity of the product. Fourth column represents the total amount of the product. And the fifth column represents the status, which means the current status of the product where the product delivery is completed, pending, or in the processing. Now, let's insert this value using the same method we used before. We copy the previous instruction code. Change the variable from product to orders. We will also update the date logic to pick a random date from the last 60 days instead of 180, and update the insert query to match the structure of the orders table. Since we are inserting more fields now, we will use 6 question mark placeholders in the values section. Each question mark is a placeholder for a value we are passing in. First, we make these changes for the product's data. Then we repeat the process for the orders data. And finally, make sure to change every remaining reference from product to order in the code. Now, let's create some additional records for the orders table. We are going to create 20 random records. Here, we are using a for loop to iterate 20 times so that we can generate 20 new order entries. Inside the loop, we will first create a variable called user ID. This will randomly select an ID from the list of user IDs we created earlier. Next, we will define two more variables, product ID and price. This will randomly pick values from the list of product IDs and prices that we also created earlier. After that, we will create a variable called quantity. This will randomly select an integer between 1 and 4, representing how many units of the product were ordered. Now, we will calculate the total amount by multiplying the price by the quantity. Then, we will assign a status to the order. This could be completed, pending, or processing. We will also set an order date. This will be a random date within the past 90 days, starting from today and going backwards. Once we have all these values, we use an insert query to add the new record into the orders table. And just like that, we have added 20 more records to our orders data. Next, we need to save all these changes. To do that, we simply type con.commit. This command makes sure that everything we inserted into the database is saved permanently. After committing the changes, we will print a message that says sample database created successfully. Now, let's print the number of records in each table. We will also add 20 to the orders count since we just inserted 20 new records. At the end of this function, we will return the open connection to the database so that we can continue working with it. Now, let's see the actual values in each table using some queries. We will create a new function and call it query examples. Inside this function, we will write SQL queries to display the data in each table. We will start by creating a cursor so that we can execute our queries. Let's also add a simple heading at the start of the function that says sample queries. First, we will print the values from the users table. We add a heading that says users, and then we run a query to select all rows from the users table. Finally, we loop through the results and print each row one by one. So with this code, we are first selecting all the data from the users table. After fetching the data, we use a for loop to print the values for each row. Now, let's do the same thing for the other tables. We will simply copy this code and make a few changes. First, we change it to fetch and print the data from the products table. Then, we update it again for the orders table. Alright, now we are going to create a main function. This function will help us perform all these operations in one place. Let's set it up. First, we need to create a connection to the database. To do that, we will call the create user store database function. Let's create a variable called con to represent the connection to the database. This variable will hold the value returned by the function create user store database. After that, we will pass this variable into the query examples function. This will allow us to check and display the values from all the tables in our database. Once we are done with everything, we will close the database connection. To do that, just type con and then we will call it to close. And that is it. The connection to the database is now closed. At the end of our script, we will print the final confirmation message. Database saved as sample database.db. Now we will write the code to execute our main function. So let's do that. With this step, the main function will run and handle all the operations needed to create the simple database that we are going to use in our database MCP project. Let's test it out. First, open the terminal and instead of PowerShell, we will use command prompt and we will type Python create sample data.py and then we will hit enter. We immediately run into an error. It says near exist syntax error. This tells us there is a typo. We have written exists instead of exists. Let's go ahead and fix that. Now that it is corrected, let's run the file again. And here we have another error. It says table orders has no column named total amount. Let's investigate why this is happening. Checking the part of the code where we define the structure of the orders table, we can see that we forgot to add the column total amount. So let's add that now. And we will set the data type to decimal. Now let's run the code again. But we are still seeing the same error. That is because we already created the database earlier, before we made this correction, and the original table did not include the total amount column. So even though we have updated the code, it is still using the old version of the database. To fix this, we will delete the existing database file. Now, let's run the script again. And this time it works perfectly. We can see the output from all of our print statements. It tells us we have 12 users in the users table, 11 products in the products table, and 26 orders in the orders table. Then we can see the actual data printed from our queries, showing the values of each table. So we have successfully created the sample database that we will be using in our database MCP project. Now, since our project is designed to handle multiple databases, we need to create another one to make sure everything works perfectly. Let's create a new file and name it createuniversitydata.py. Inside this file, we will write the code to create a university database. The structure will be almost identical to what we did before in the e-commerce database. So we have already prepared the code for this in a notepad to save time. And now we have the code in place. While the structure is similar, the tables and values are different because this is a university database. As we can see, it connects to or creates a database called universitydatabase.db. Now earlier we named our first database sample dataset instead of sample database. Let's fix that too for consistency. Since we have corrected the name, we will go ahead and delete the old database file. And now let's execute this file again. Now that we have our database with the correct name, let's go through each part of the university database and see what changes have been made. In the university database, we have a students table that contains record of the students. It includes a unique auto-incremental ID for each record, a student ID which must be unique and not null, and fields for the student names, email, and age. The major column represents the subject the student is majoring in. The year level column indicates whether the student is a freshman, sophomore, junior, or senior. There are also fields for the student's GPA and enrollment date. Next, we have the professors table. It includes a unique auto-incremental ID for each record of the professors table, a unique professor ID, name, email, and department. The title field specifies whether the individual is a professor or associate professor or something else like assistant professor. Additionally, the table contains the professor's salary and hire date. Then we have the courses table, which stores information about the different courses offered at the university. This table includes a unique auto-incremental ID for each course, a unique course code which cannot be null. It also includes a description of the course content, the number of credits, and the department offering the course. The professor ID column links the course to the professor teaching it. We also store the semester and year the course is offered, along with the max student columns to specify the maximum number of students who can enroll with the default value of 30. Following this is the enrollments table, which tracks which students are enrolled in which courses. It includes a unique auto-incremental ID for each record, along with student ID and course ID fields that serve as foreign keys, linking to the respective students and courses tables. There is also an enrollment date column that stores the timestamp of when the enrollment occurred, using the current time as the default. A grade field stores the student's grade if available, and a status column defaults to enrolled, indicating the enrollment status. After defining the table, we insert data into the student's table, just as we did in the sample database. For the professor's table, we follow the same process. Next is the courses table where we randomly assign the maximum number of students that can enroll in a course. Finally, we insert values into the enrollments table. This code is used to add 30 random student enrollments into the database, but only if the student is not already enrolled in the same course. It randomly selects a student in a course, checks whether that combination already exists in the enrollments table, and if not, it assigns a random grade like A, B, or C, and a random enrollment status like enrolled, completed, or dropped. In this part of code, if the student's enrollment status is enrolled, it means the course is still ongoing, so no grade is assigned yet. That is why the grade is set to none. Then it generates a random enrollment date within the past 1 to 180 days. Finally, it inserts the student ID, course ID, grade, status, and enrollment date into the enrollments table. Then we will perform commit operation to ensure that whole student, professor, course, and enrollment records are permanently stored. After that, it prints a message confirming that the university database was created successfully, and it displays the number of students, professors, and courses added. It also shows the total number of enrollments, which includes both the original ones from the data list and the 30 additional random enrollments generated earlier. In the queries section, we run queries to print the values of the tables. Name and some additional queries to retrieve the student's name, course code, course name, grade, and enrollment status by joining the student's enrollment and courses tables using their respective foreign keys. The results are ordered alphabetically by the student's name and then by course code for clarity. We also show the courses along with the names of the professors teaching them. This query retrieves the course code, course name, and professor's name by joining the courses and professors tables through the professor ID foreign key. The results are ordered by course code to keep the list organized. And after this, everything remains the same. Now let's run this code and see how it performs. Type Python create university data.py and hit enter. We haven't got any output. Let's check if code is working correctly, particularly the function call. Everything looks fine here. The issue is that we did not save the file after pasting the code, which is why there is no output. Let's save the changes by pressing Ctrl S, and now the code will be saved to the file. Now run the code again. This time we have got an error saying unique constant failed. It points it points to the users table, which should not be in our code. Let's check if it is present. We don't find this code in our current file. To It seems to be in the sample database file, and the error occurred because we accidentally ran that file, which tries to insert a value into the email column that is supposed to be unique. Let's now execute the correct university database file. And now we have got our expected result. Next, we need to add this university database to PostgreSQL so we can connect it to our database MCP. Let's open pgadmin, which is the graphical tool for managing PostgreSQL. Once it is opened, go to servers. In this case, we have a server named PostgreSQL. Click on it. There is a databases section showing all the databases we have created. Here, we can see databases like Ecuador Analysis, HousingDB, Original Database, and others. Inside the original database, under schemas, there are 4 tables. One of them is customers. Now let's create a new database for our university data. Right click on databases, then click create and provide a name for the new database. And then save it. After opening it, go to schemas and then go to tables, and we will see that there are no tables yet. Let's add tables to this database. First, we will create a file named university data pgsql.py. In this file, we will import SQLite 3 to connect to the university database.db file. Then we will import pandas to perform data frame operations. Finally, we will use SQL Alchemy, which provides the create engine function to create a PostgreSQL engine pointing to the database running on localhost with the appropriate user, password, and database name. We will understand this better in a few minutes. First, we will connect with the university database through SQLite. Then we will create a SQL alchemy engine for the PostgreSQL. Here, first, we will write PostgreSQL as we want to connect with PostgreSQL database. Then we have a username Postgres. After that, we will add password to the PostgreSQL, and then we will add port number 5432, and after doing that, we will add the name of the database, which in our case is University Database. To get the port number, we can go to the server named Postgres 17, and then we will right click and it will show an option of properties at the last. After clicking on which, we will get this connection tab where the port number is mentioned. Now let's go back to the code. Here, first, SQLite cursor creates a cursor object, essentially a control handle for sending SQL commands through the existing SQLite connection. Cursor execute select name from SQLite master where type is set to table, runs a SQL statement against SQLite master. That is a special system catalog that stores metadata about every database object. The query filters for rows where type is table, so it returns only the user-defined tables, not indexes, views, or other objects. Finally, cursor fetch all collects the entire result set into tables, which becomes a list of tuples, each tuple containing the name of one table present in the database. Then we will print how many tables we have found. After that, for each table, we will first get the table name, which is at index 0. And then we will select the table from the SQLite connection and read the data as pandas data frame. After doing that, with the help of pandas functionality called toSQL, we will migrate the data to PostgreSQL. If the table is already present in the PostgreSQL, it will be replaced with the new one. We don't want the data frame index to be added as a separate column in the table. By using the multi method, instead of inserting one row at a time, we insert many rows at once. Then we will print the table name that has been migrated and how many values has been migrated. At the end, the migration will be completed and then we will close all the connections to SQLite and PG Engine. Close it for SQLite, we will write SQLite con and then we will call the close. And for the PG engine, we will write PG engine and then we will call the dispose. Now we will run this code through the terminal. Let's activate the virtual environment we created for this project. Now let's run it again. It is still giving the same error. Let's install pandas as well as SQL Alchemy. Now let's run the script again. This time we get an error because we accidentally typed 2s in PostgreSQL. Let's correct that. The error message now says that a particular library is not installed. Let's install that library as well. Now let's run it again. This time it executed successfully. We can see the output from the print statements. Next, let's check PostgreSQL to see if the tables have been migrated. At first, the tables are not showing. Let's refresh. And now we can see our tables. The column names are also visible. Let's right click on the database and open the query tool to check whether the values have been inserted into the tables. We will run a simple select all query to view the contents of the table. Here we can see the data in the students table. We will repeat the same process for the other tables. So we have successfully migrated all the tables to PostgreSQL. Fantastic. We have successfully created our foundation for the database MCP project. First, we set up our development environment with all the required libraries. Next, we created an e-commerce database with users, products, and orders tables. Then, we built a university database with students, professors, courses, and enrollments. And finally, we migrated our university data to PostgreSQL. We now have two databases, which will be perfect for testing our database MCP server's multi-database capabilities. In the next part of the series, we will start building the actual MCP server that can intelligently connect to and query these databases. We will see how Claude can seamlessly switch between databases and provide intelligent responses about our data. If you need help with your projects, have difficulty learning these concepts, or want to deepen your understanding of how things like this work, Codersarts is here to support you. We offer personalized project assistance, one-to-one live sessions, help with building AI-related applications, and full development and deployment services. Visit us at www.codersarts.com or reach out directly at contact@codersarts.com. You will also find our LinkedIn, Instagram, and Facebook handles linked in the description box below. Thanks for watching, and don't forget to like and share the video and subscribe to the channel so you never miss out our latest tutorials. Thank you.